is an old definition of a mathematician. A mathematician is a machine changing coffee into mathematical results. And well, that's exactly Yuri. Well, to say a few words, he's originally from Ukraine, but living in Poland for many years. And well, his field of interest is not so narrow. Well, he has quite nice result in many directions of operator theory. And one thing more, he's not only writing papers, but he's also reading, which is not so automatic these days when the number of papers is exploding. Well, today he's going to speak about one of his favorite topic, which are semigroups of operators. And well, the title is on the screen. So please start.
Thank you, Vladimir. Today I will speak about recent advances in theory of functional calculi for mostly semigroup generators, but not only, also in a discrete setting. And in a sense, my talk will be an extension, a complement of a plenary talk by Charles Beatty, which he gave during last IWOTA in Lancaster. I mentioned a number of new results obtained just last year, and also put a little bit different emphasis. Let me start first with the digression. So imagine that we have a holomorphic function at the neighborhood of some domain. Then, as everybody knows, a function can be recovered by this Cauchy formula, and well, this reproducing formula is behind of basically complex analysis. Okay, so if you would like to now to define a function of operator, a naive way to do this is just to replace independent variable here by an operator, yeah, and to plug in A instead of Z. So, and then is this way we get a Ries-Danford functional calculus. Actually, this is, of course, very naive, very banal idea, but it works in many circumstances, and actually we will see today many manifestations of such an approach. It really looks naive, but strange enough, it's universal. Just plug in A instead of independent variable, use reproducing formula, and basically you have a calculi. Although the formula is not always obvious, for example, look at this formula, which gave rise to very useful Dynkin-Helfer-Stjorstrand functional calculus. Sometimes people add the name of Davis. Here, you don't require any analyticity, so function should be smooth, just neighborhood of the domain. And the formula has an analytic part, which is here, and a part which measures deviation from analyticity. Yeah? So if function is analytic, then we have no second part, and we have just Cauchy formula. Curiously enough, such a formula may define a homomorphism, may define functional calculus. If you look at this properly, and actually just Cauchy-Green formula. Yeah? It's an example of non-obvious approach to this Banach idea, but let me now continue with a reminder on semigroups. I guess many people are not aware of basics of semigroup theory, and I'd like to continue with really a short introduction to semigroups, and I hope that experts in the audience will excuse my service to community. So what is a semigroup? It's just strongly continuous functions, yeah, divided on R plus with values and operators, which satisfy semigroup law, and actually it's also should be normalized at zero to be identity. And the notion of semigroup is not is inseparable from the notion of generator, which is defined as the right-hand side derivative of semigroup at 0 on the natural domain. And vaguely, one can look at the semigroups as the operator exponential, but only to some extent. And actually, a major problem in semigroup theory comes from the fact that actually semigroup is not an exponential of generator, actually source of many problems. And then, for this talk, it would be convenient to work not with generator, but with a negative generator, and to say minus a generator. Why? Just because basically function spaces live on upper half plane or right half plane. Yeah, generators live on the left half plane. And just to avoid problems with sign, so I just work with such a strange notation. This is the first look. Why semigroups are important? The importance of semigroups comes from the fact that the one-to-one correspond to well-posed problem, well-posed abstract Cauchy problem, and well-posed abstract Cauchy problem one-to-one correspond to well-posed PDE. So actually, to study semigroup in essence is the same to study PDE. And well, I think it's of major importance and really nice motivation for semigroup theory. Unfortunately, semigroup theory is fading out nowadays by some strange reasons. Yeah, and well, one-to-one correspond, and then the illustration of this is just actually all smooth or classical solution of the problem can be described by the orbit of the semigroup. So two remarks. The first remark is if you have a bounded semigroup, then the spectrum of generator, binary generator in the right half plane, called right half plane. And the second thing, actually, that's a resolvent of the generator is the Laplace transform of the semigroup, and actually fundamental relation, which behind actually the whole of theory, and it's very instructive to have this in mind. Now, after this short introduction, let me consider the algebra of bounded measures on the half line. And let me apply Laplace transform to it. What I get the algebra of Laplace transform of measures. And now a function algebra living on the closed right half plane, and with a norm, with a natural norm induced from the algebra of measures. Yeah. Then I would like to define a functional calculus just based on this algebra of Laplace transform. How to do this? Just use Laplace transform. I'm plugging A instead of Z, plugging A as an independent variable, so just use reproducing formula, yeah? And in this way, we get a very classical functional calculus called the Healy-Phillips functional calculus, which is omnipresent in many issues of semigroup theory, and it is in any good textbook on semigroup theory. It is very well known, very well understood. Unfortunately, it has several major drawbacks. And the most important one, actually, the norm estimates arising from this calculus are really very, very rough and quite often are far from being sufficient. Then, of course, it's very difficult to recognize when the function given a function of Laplace transform, and actually the whole of algebra of Laplace transform is very small to be sufficient for many purposes, for example, arising in PDE. So there's a need for better calculus. Unfortunately, there was no progress in this direction until very some time, but the situation has changed quite recently. And I'd like to stress that, of course, there are many calculi dealing with unbounded operators. And here's calculus is bounded. The classical sense is bounded homomorphism, yeah? And as far as the bounded homomorphism, that produces a norm-estimate. Okay, now to put our theory, our new theory in the proper context, I should recall some brief history of relevant statements. There are many of them, and I just review several milestones, and I would like to start with the fundamental paper by Vladimir Peller, written in the beginning of the 80s, where Peller tried to address famous Halmos similarity problem solved eventually by Pizier. So to start, we define a quite curious space of holomorphic functions, the unit disk. How we define them, we consider the derivative of function homomorphic in the unit disk over concentric circles, take L infinity norm, and the function obtained in such a way should be integrable over the radius, so should belong to L1 over 0, 1. So such a space is included in the disk algebra, and we can make Banach algebra out of it by posing an appropriate Banach algebra norm, which is sum of the infinity norm plus the semi-norm defined at the top of my slide. So what Peller did, first of all, he provided really sharp estimates for polynomials of power-bound operators on Hilbert spaces. Yeah. So he figured out that the norm of polynomial of power-bound operator on Hilbert space is dominated by the norm of the polynomial in the this algebra B times universal constant dependent operator. And then if you calculate or estimate the norm of polynomial in algebra B, then you can kind of measure deviation of operator from polynomial boundness and deviation of the logarithmic size. Yeah, is logarithmic size like here. And I should, of course, remark that actually, well, how to come to the algebra. Actually, Peller had in mind Bessel spaces on the unit disk, usually defined by Littlewood-Pellet decomposition. And actually, he worked with the isomorphic copy of the standard Bessel space described by the boundary behavior of an identity function on the unit disk. So having such an estimate, as far as polynomials are dense in this algebra B or dense in the appropriate Bessel space, so we may create a homomorphism from B of D to the space of operators by just closing the set of polynomials. And of course, here, again, a drawback, actually homomorphism is not explicit. Yeah? We close polynomials, but we don't know how homomorphism look like. So if we would like to handle some specific function, then we'll have problems. Unfortunately, Peller missed this point, and this point was clarified very recently. This paper generated a number of various generalizations, in particular due to Bourgain and due to Pizier, who simplified several arguments from Peller paper. And then, of course, a natural question is how to find a substitute for the half plane, how to find a substitute for semigroup generators. And then, first of all, one should find an appropriate substitute for Bessel space for algebra B of D. The definition is complicated, just at the top of my slide. So here you have a classical definition in terms of Littlewood-Pellet decomposition, which somehow I adopted for the purposes of my talk. It's not very standard. I'll skip the discussion of the definition just because of lack of time, and actually we don't need it, but the thing to take home, actually the definition is really very complicated, and if you put a norm on such a version of BAD of a unit disk, then the norm is becoming quite difficult to handle. Unfortunately, people used such a version of Peller space, such a version of the same Bessel space for the half plane, and with such a version, they proved a counterpart of Peller's theorem for operators satisfying a really very, very strong resonant estimate. Like here, one may say that there are proofs made for generators with bounded, sectorially bounded holomorphic semigroups, but we may skip semigroup terminology. So such an estimate, such a counterpart of Peller bound, was obtained by Witze in 2005, and then it was a little bit improved by Felix Schweninger, actually in a nice paper written in 2016. A funny story, actually, is a number of generalization of parallel results were obtained in the thesis of Stephen White, written actually in 1999, but White didn't publish thesis. He went to teach to school. Theses were lost, and they were discovered just several years ago. Very nice thesis, very deep one, but unfortunately, well, such a strange story. And actually, a major breakthrough afterwards was done by Markus Haase, who is unfortunately not here. So he obtained a counterpart of parallel results for generators of bounded semigroups and holomorphic, bounded semigroups and Hilbert spaces. And then, unfortunately, he used the same Littlewood-Perry decomposition norm, which was quite inconvenient, and he obtained estimates only for a Laplace transform of bounded measures. It's not possible to extend it further. It's not possible to extend the estimate further just because Laplace transform are not dense in the Littlewood-Perry version of vector space. And it's not clear how to proceed. And then there was a really huge activity around this topic, but still crucial problems remain unsolved. First of all, how to construct a really calculus on the whole of the space, how it looks like, what is homomorphism. And the second thing is how to estimate such a complicated norm, yeah? Because even if you take a simple function like this one, yeah, realizing Cayley transform, it's really very, very hard to provide any reasonable estimate in such a way. There are many other questions, but the first two are the major ones, and today we'll explain how to settle them. But to really appreciate the result, to really have some flavor of what's going on, let me start with several observations. And I would like to recall a very useful result proved by Sasha Gomilka and Tuchanish and Feng on the eve of the last century. Actually, the result provides a characterization of generators of bounded Hilbert space semigroups in resolvent terms, yeah, in terms of means of the squares of resolvent. So I should recall that actually generators can be characterized. There is a classical Hill-Yoshida theorem, but the theorem is so complicated one can never apply it really in the real life. And this is quite a handy result, which can be used in many of the constructions and will also be helpful for us. So now recall that actually the square of resolvent is a derivative of resolvent modular sign, yeah? And so it's natural to introduce a space of holomorphic function on C+, defined just by very similar expression as a Gomilka-Shifan condition. And then what the condition, the resolvent condition said, actually that all weak resolvent of our generator are somehow sitting in the space E just introduced. Yeah. So the space E accommodates all of the weak resolvent. As far as the space E accommodates all of the weak resolvent, then natural guess to try to put a norm on the space E, yeah, to consider a dual of E paired with E with some duality, and to try to kind of imitate, to mimic the Cauchy formula in this way, yeah. And actually it's a kind of duality approach to functional calculus, not so very well known, but it was advertised by some people, also by Nikolsky in some other situation. And this guess appeared to be quite correct, at least to something interesting. But let us have a closer look at the space E. So we observe that actually functions from E have a limited infinity, and then actually they included into the space of a Laplace transform bounded function as quite an instructive remark. Then E can be normed in such a way, and just for intuition, I would just remark the Cauchy transform of bounded measures on C+ are in the space E. Now, one should try to find some space which should be paired with E, and a natural candidate is just a counterpart analytic functions counterpart of the Peller space. And then to pair both spaces, we introduce the next duality, which is easy to show to be bounded. At first glance, the duality looks a little bit artificial, but if you look at the definition of E, a definition of space B, counterpart of Peller, then you'd see just, well, it's immediate guess how it should look like. And actually, it appears that it's not artificial, because actually, as observed by tables and also Featherman-Stein, by just using Cauchy-Green formula, you may rewrite this duality in just a conventional way. Yeah? So by greening our duality, we get a usual duality, but for just functions satisfying some additional requirements just to make green formula work. Okay. Now we should look a closer look at the space B, and then once again I should remark that there exists a limit at infinity. There are also very nice boundary values. That's why actually I defined B dyadic in a standard way. And then Laplace transforms are also included there, but as I already mentioned, the space of Laplace transform is not dense in B, and also not closed. So by introducing norm appropriately, we make B a Banach algebra. And actually what is important, this space B appeared to be isomorphic to space B dyadic used by people, this bad B dyadic space. Now, actually, that's the key point. It appears actually the space B allows a reproducing formula in terms of our duality. So that's basically just a Cauchy formula, yeah? In disguise. Just we write Cauchy formula in a special duality introduced just several seconds before. Now we can write in an explicit way, and we get a nice explicit formula, explicitly reproducing formula of function from B. So the formula is really nice and can be applied in many circumstances. So first we saw that actually we found it, and this is double integral really our invention, but actually it appeared it was advertised by some famous people before, again like a nice formula, for example, by Koifman and Mayer. And again, I should remark that by using green formula, yeah, for nice functions, we can transform this, let's say, generalized Cauchy formula into just usual Cauchy formula, yeah? So that's a Cauchy formula under really thin disguise. But to obtain such a reproducing formula is a really huge business, and the proof is really very, very complicated. Now let us follow the standard strategy. Yeah, so we have a reproducing formula, just plug in A instead of independent variable. Yeah, insert A instead of Z, and then we get a functional calculus. Very explicit formula, first of all, given by resolvents of the generator. That's a well-defined boundary homomorphism, and so we have function estimates in terms of the norm of the function in B, which are computable very easily, well, comparatively easily with respect to the other calculi. Moreover, the calculi has a number of nice properties, actually all of the calculi properties. Permanence, Perker-Lopin theorem, convergence properties, etc., etc. I will not mention them. So we were happy with this. And actually, via this calculi, we reobtain or improve virtually all existing estimates in the literature for Hilbert space semigroups. Here is an example which concerns the powers of Cayley transform. So you have a bounded semigroup on the Hilbert space, you consider the power of Cayley transform, and you ask what is the best possible bound. Yeah? For contraction semigroup, of course, there's a classical fact that actually Cayley transforms again in contraction, and then that's behind Notch Foyer's approach to semigroups of contraction. But what about bounded semigroups? There was a huge activity around such question, and the best possible estimate at the moment belongs to Sasser-Gemilke, obtained quite a long time ago in a very complicated way. Now we derive it in a simple way. It's open whether the powers are uniformly bounded. It's an interesting question. I will skip the discussion. But let us compare the classical functional calculus and the B calculus. Yeah? And you see a huge gain we get by just using B-norms. And such an effect present in all possible estimate I approach. So if you know any funny estimate, just tell me, I'll try to use B-norm. Moreover, our calculi allows to revise the whole of semigroup theory just because what is the exponential as Laplace transform of delta function. Yeah? So you replace exponential by Laplace transform, for example, of measure, and then you can really obtain B statements of all semigroup facts. Well, just a simple example that I mentioned, the classical Geerhard-Pruss theorem. Yeah, it's here. Geerhard-Pruss theorem gives the criteria for so-called exponential stability of the semigroup, but we can do much more. We replace exponential by B function, and then we get really much more than Geerhard-Pruss offers. Moreover, using B calculus, we get new spectrum mapping theorem. I should recall that in general, spectrum mapping theorem doesn't hold for exponentials, but for special functions from B, for example, for Riemann measures, we do get spectrum mapping theorem. And this fact can be used in various issues of semigroup theory related to spectrums. Again, there are a number of interesting questions around these facts, around other generalization. I skip this. And the next question arises, okay, so we obtain our B calculus under some assumptions. Yeah? So boundness of semigroups. So are we doing the right thing? Are we able to improve a little bit what we obtain? And the answer is no. Our calculus is optimal in a really strong sense. So to realize this, let me define the calculus in an abstract way as a homomorphism acting from algebra B to the space of boundary operators. Now on Banach spaces, for example, now we don't care much, and what we can prove, that if the generator admits a B calculus in abstract sense, yeah, as a homomorphism, making resolvent functions a resolvent of A, then the resolvent property holds. And in particular, then minus A generates a bounded semigroup. And in this way, one may say that minus A generates a bounded Hilbert space semigroup if and only if A admits B calculus. Yeah. So we don't lose anything. Moreover, the calculus given by our duality formula is unique. So the calculus is best possible. I should say that actually the space E is omnipresent in all our arguments or our considerations, so it's not present in the formulation. I should underline actually neither E nor B are dual to each other. But it's enough to have a partial duality between them. It's enough to know that one of the spaces is a part of the dual, and to use some special weak topology to argue with operators and functions. That's a really subtle moment. I've never seen it before, but it's quite useful to have in mind. Now, it's really natural to mention some limitation of B calculus. It's not a nice calculus, but nevertheless it has some limitation. It's really Hilbert space calculus, and the corollary here understands this point quite well. So if you consider the semigroup of right shifts on OP, then the generator admits a B calculus if and only if P equal to 2. Yeah. So it's very difficult to transfer the calculus, let's say, to the setting of OP space, and I think it's not possible. Then as far as we have such a nice calculus, it's natural to think about generalization. All generalization appeared either this year or last year or 2 years ago. First, it's possible to transfer this calculus to, again, to the setting of the discrete the discrete set into power bound operators, and to improve Peller, and such a transform was done by Arnold independently by Betty and Seifert, who improved Peller by providing a reproducing formula for such a calculus. And this reproducing formula allowed to obtain a number of additional properties of the calculus, very interesting ones, for example, to prove new version of Carstensen-Friedrich theorem. Peller, as I mentioned, just missed that. So he was happy with polynomials, but as I underlined many times, it's useful to know reproducible formula. So one proves such a formula for functions and plug in t instead of independent variable, and you're done. You have a homomorphism. Then, quite recently, another generalization appeared due to, again, Arnold and Christian Lemerdy, who actually extended our calculus to a larger algebra, to the so-called Figaro-Talamanca-Hertz type algebra. The definition is on the slide. I wouldn't comment on it just because of lack of time. But the thing is, they proved a theorem saying actually that if you have a generator bounded Hilbert space, then it allows a calculus on the strictly larger algebra. Strictly larger algebra, and we have a kind of Tauberian theorem. If you have a B calculus, and you have a calculus on larger algebra constructed by Arnold and Lemerdy. In general, it's a nice, quite curious result. Use a number of interesting Banach space theory, theory of projective tensor products, multipliers on the H1 spaces. But the thing is, the norm is really unobservable. It's very difficult to play with. And apart from this statement, they prove just nothing. So no spectral mapping property, no estimate, just it would be very interesting to realize whether it's possible to find an isomorph of such an algebra in terms of complex analysis, in terms of space of analytic functions living on the right half plane with special boundary behavior. Unfortunately, the question seems to be really very, very difficult, and nobody addressed such a matter. Actually, even Bessel, classical Bessel spaces, as far as analytic functions are concerned, and as far as half-plane concerned, are not well studied, and there are many overprobable there. Finally, Vladimir, I probably speak too. Okay? Sorry, I realize that I am speaking more than I should. Okay, I finish quickly. There is an extension, in a certain sense, our approach to so-called sectorial operators, which became quite popular last decades. So basically, you might say that you are dealing with generators of bounded homomorphic spherical Banach spaces, but not only, actually. That's, if you can play with angle here, it's quite a general class. So what is sectorial operator? So the operator which having spectrum in the sector and having a best possible estimate on the resolvent outside of any larger sector. Then we may define an appropriate algebra on the sector, so-called Hardy-Sobolev algebra, so either algebras with the derivative in the Hardy space H1 on the sector. And then, following our naive approach, obtain a reproducing formula, plug in A, and you have a homomorphism. We really obtain a new calculus, which we called psi calculus. And the thing is, we really get a formula which looks interesting because of this kernel. Yeah. I have no time to explain what is this, but nice properties of this kernel allow to actually, well, first of all, to rewrite the theory of homomorphic semigroups in a simple way, but it also allows to obtain much more. And I would suggest to look at this formula closer, because this inverse cotangent, I think, has a nice potential. And one may get, actually, there's a reproducing formula in the scalar case, also new, and then you just plug in operator. Well, nice estimate, nice formula, and this activity continues. I think it's interesting, and we expect more interesting things to come very soon. So thank you much for your attention. Sorry for talking for so much time, actually. I'm really sorry. And just last but not least, as far as my talk is almost the last one, I'd like to thank organizers, Marek, Ptak, Michał, Wojtylek, and the rest of the team for organizing very nice, very inspiring conference. I think it was really enjoyable by all of us. And I also would like to thank them for inviting me to speak today, on Saturday. So thank you much.
Thank you very much for a very nice talk. Actually, well, this watches, clock is too fast. It's not so bad with the time. Anyway.
Too fast, you think?
Are there any questions? Yes.
So these very nice applications of these very nice theorems to uniform exponential stability of semigroups. Is there any possibility, it might be a silly question, to use it for point-wise stability along orbits somehow? Could say results. If something, then...
Yeah, sure. Sure, for example, you are interested in, let's say, in access from some domain of the generator, like fractional power. Then you multiply by the inverse, like a plus z to the power minus alpha, then you get b function, estimate the norm, and then you're done. Just 2 lines proof.
Okay, next question, please.
Yeah, nice talk. Just to fix ideas, I wanted to know that your B calculus, if applied to the generator of the shift semigroup on L2R plus, do you know exactly what it is?
You mean whether the calculus is compatible with, let's say, Notch Foyer's calculus? I mean, you have a contraction semigroup, and you have a very nice H infinity calculus, which is the best possible. You have H infinity norms there, yeah. The problem comes when you don't have contraction semigroup. I should underline, okay, I speak about bounded semigroup, but any semigroup can be made bounded by shifting by exponential, yeah? And then basically the calculus can send all of the Hilbert space semigroups. Of course, in discrete case, when you multiply t by lambda, you get an operator with spectral radius less than 1, and it's not so interesting to have calculus, let's say, of dealing with analytic functions on a much larger sense in the spectrum. But for semigroups, the situation changes, and for them, actually, such a shift really makes a sense. Okay, thank you.
So it agrees with the H infinity functional calculus?
Again, it applies, of course, to shift semigroup, but there are much better calculus like H infinity calculus, and there is no sense to apply it because it provides much worse estimates.
Other questions, please? Well, if not, let us thank the speaker once more again. And we have a